In this lecture, we're going to learn about confidence intervals for proportions or for the probability of something occurring. This will allow us to understand how those polling companies compute things like something is accurate with a margin of error of plus or minus 4%. To start off, let's remember again that example with flipping the bottle caps. If we flip a cap 1,000 times and get 576 red, what does that tell us about the true probability of getting red when you flip the cap? Well, if we let P stand for this unknown but true probability of getting red when you flip the cap, then we could estimate P just by the proportion. So the estimate, which we'll write as P hat again, is 576 divided by 1,000, or 57.6%. But the question is, how confident are we? How sure are we that P really is how close to 57.6%? Well, with everything we've learned so far, we can figure this out. We already know that the distribution of P hat has a mean and a variance. In fact, the mean of P hat, or expected value, is equal to P, so that's good. The variance of P hat, well, we worked that out previously, and that works out to P times 1 minus P all divided by N, where N is the number of samples, which in this case is 1,000. Now we also know the central limit theorem, and it tells us that since P was made up of an average or a proportion of lots and lots of flips, that it approximately follows a normal distribution with this mean and variance. That is, we can say that P hat has a distribution approximately which is normal with this mean and this variance. Now we can do a little bit of manipulation. If we subtract off the mean and divide by the square root of the variance, then we get a quantity which has approximately the standard normal distribution. Now, the standard normal distribution is something we know all about. We can graph, and we can get the probabilities for it too. For example, it turns out, for the standard normal distribution, that the area under the curve between minus 1.96 and plus 1.96 is just equal to 95% of all the area. So it means usually, if you have a normal distribution, you'll be between minus 1.96 and plus 1.96, which means that only 5% of the time will you be farther away than that. So in other words, the probability that this quantity, which has approximately a standard normal distribution, will be more than 1.96 is approximately equal to 5%, or equal to 0.05. Now when we rejig this and work it all around, we end up by concluding that the probability that P is between P hat minus 1.96 times the square root of P times 1 minus P over N, and P hat plus 1.96 times the square root of P times 1 minus P over N is about 95%. Now, this is what we will call a 95% confidence interval. We're saying that we're 95% confident that the true unknown value of P is somewhere in this interval. Now, of course, the true value of P isn't random. It's really more P hat that's random because we did a random sample by flipping that bottle cap over and over again in order to try to compute it. But nonetheless, we call this a confidence interval, and we say we're pretty sure that P is within this range, or at least that the probability it's outside this range will be only 5%. Or in other words, 19 times out of 20 it'll be within this range. Only 1 time out of 20 will it be outside this range. Now, if we understand what we did for the bottle cap, then it's easy to do it in general. We can say if we have any experiment with a certain probability of, let's call it success, like getting red, let's say, and if we experiment and get n different experiments or trials, and then we say, well, let's look at the proportion of successes, so the number of successes divided by the number of trials, we'll call that P hat. It's our estimate of the true probability of success on each trial. And then we still know the mean and variance, just like in the previous example. We can still rewrite everything and end up with this same formula that says that the probability is 95% that the true value P is between P hat minus 1.96 times the square root of P times 1 minus P over N and p hat plus 1.96 times the square root of p times 1 minus p over n. And this gives us, again, the 95% confidence interval. There's a few other things we can say here. One is, you might think this isn't that useful because, after all, the confidence interval has p in it, but p was unknown. Well, there's two ways to proceed there. One is we could say, well, p is probably pretty close to p hat, so let's just kind of substitute in p hat instead of p. That's often done. Another thing that's done, as we'll see in more detail in the next lecture, is to say, well, this can actually be bounded by substituting in when p is a half, because that's the widest interval that we could get. So what it means is that we can use as a confidence interval that same interval, but this time substituting in when p is a half, and that gives us a slightly wider confidence interval, so we're being a little bit cautious or conservative, but it's actually very useful, and this is what's often done. For another example, let's talk about a public opinion poll. So here's an opinion poll from a recent United States presidential election, and it talks about the percentage of support that each of the candidates had when they did their survey, and at the end it says, oh, it had a margin of error of plus or minus 4%. Well, now that we understand confidence intervals, we can understand what they're saying. Indeed, if we remember that formula for the confidence interval, we had that range was between p hat minus something and p hat plus something. Well, that something is often called the margin of error. And indeed, if we compute in this case, we can say, well, the margin of error, when we stick in the conservative assumption that p is a half, then we compute the margin of error to be just a little bit more than 4%. So that's why that opinion poll said that the margin of error was plus or minus 4 percentage points. They meant that when you compute the half width of the 95% confidence interval, that it does indeed work out to be approximately 4%. Now you might think, why do we have to stick